Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. So I want you to imagine for a moment a massive container ship crossing the Pacific.
Oh, yeah, right out in the middle of the ocean.
Exactly. Deep down in the bowels of that ship, connecting a towering diesel engine to the propeller, is a solid steel drive shaft. And it's basically the size of a redwood tree trunk.
Right, and it is just spinning relentlessly, delivering, what, tens of thousands of horsepower?
Tens of thousands, easily. But then suddenly, something catches. The propeller encounters this immense resistance. And in a fraction of a second, that massive steel shaft twists like a wet towel and violently shears in half.
Leaving the ship completely dead in the water. Yeah, it is a terrifying scenario.
It really is.
And unfortunately, it's one that is entirely grounded in the physical realities of how materials behave under extreme stress. I mean, when we talk about engineering, we often picture static things,
Hey, like blueprints or concrete columns, perfectly straight steel beams.
Right, exactly. But the reality is that every single material we use is engaged in a constant, invisible war against the forces trying to tear it apart, twist it, or crush it.
And that invisible war is exactly what we are unpacking in our deep dive today. We've gathered the most popular, just burning questions that engineers and students are asking online about the fundamental behaviors of materials and structures.
It's a great topic.
Yeah, and we are treating this material like an absolute masterclass. Our mission today is to start at the microscopic level, like looking at a single crystal of steel and scale, all the way up to how modern global teams of engineers actually use complex software to manage these forces.
Long before a single piece of metal is ever even cut.
Right. So this is really the ultimate journey from the raw, unyielding physics of stress and strain to the highly adaptable digital workflows of concurrent engineering.
Which is fascinating because the mathematical laws governing that ship's drive shaft, they haven't changed since the 17th century.
Well, really?
Yeah. But our understanding of why materials fail and how human beings collaborate to prevent those failures, that has completely transformed.
Okay, well, let's start right at the beginning then, at the absolute foundation. If you want to understand how a skyscraper stays standing, you first have to understand what happens when you simply pull on a piece of wire.
Right. The absolute basics.
Yeah. Back in 1678, the scientist Robert Hooke conducted this beautifully simple experiment. He basically hung a long wire from the ceiling and started hanging weights on the bottom of it.
A very classic setup.
Right, and he noticed that if he added a small amount of weight, the wire stretched a little. If you doubled the weight, the stretch doubled. It was this perfectly proportional relationship.
Which gave us Hooke's law. It sounds deceptively simple, but what Hooke was actually observing is what we call the linear elastic region of a material.
Okay, break that down for us.
Well, to really understand what's happening there, you have to zoom in on the atomic structure. Metals are composed of a vast number of tiny interlocking crystals which form a lattice.
Like a microscopic grid.
Exactly. When you apply that tensile load, when you hang that weight on the wire, you are physically pulling the atoms slightly further apart. You're distorting that crystal lattice.
But the key word there is elastic, right? I mean, if I stretch a rubber band and let go, it snaps back. Is the steel wire doing the exact same thing?
Under small loads, yes, absolutely. As long as you stay within that linear elastic region, up to what we call the limit of proportionality, the material acts exactly like a spring.
So the atoms are stretched but not broken.
Right. The atomic bonds are stretched, but they aren't permanently rearranged. So when you remove the weight, the atoms pull themselves back to their original resting positions.
Meaning the wire returns to its exact original length.
Precisely.
Okay, so if it's acting like a spring, that means I'm putting energy into it. Like if I pull back a bowstring, I'm storing energy in the limbs of the bow. Am I storing energy in a steel beam when I put a load on it?
You absolutely are. Because the deformation is totally recoverable, the mechanical work you do by hanging those weights is stored inside the molecular bonds of the material.
Ah, as strain energy.
Yes, recoverable strain energy. If you were to graph this, say, putting the load on the vertical axis and the extension on the horizontal axis, you would draw a perfectly straight angled line.
Like a ramp.
Right, and the area of the triangle underneath that line, that represents the exact amount of strain energy stored in the material. You are effectively charging the metal like a mechanical battery.
That is such a cool way to think about it. But obviously, you can't just keep adding weights forever.
No, you definitely cannot.
Right. Eventually, something has to give. You hit a point where the spring doesn't snap back.
Yeah, you reach the yield point. And this is where the behavior of the material starts to tell a very complex story, because different materials yield in very different ways.
Right, and the source material for our deep dive today spends a lot of time discussing one material in particular because of its incredibly dramatic yielding behavior.
Annealed mild steel.
Yes. But let me pause you right there because I want to make sure we define our terms for everyone listening. What exactly does annealed mean in this context? Why not just say mild steel?
Oh, that is a crucial distinction. Annealing is a heat treatment process. When steel is manufactured or rolled or drawn into a wire, it builds up all sorts of messy internal stresses.
It gets all tense and mangled.
Exactly. The crystal lattice gets all messed up. So
Yeah.
to get a true, pure baseline of the material's properties, engineers heat the steel up to a very specific temperature and then let it cool down incredibly slowly, usually inside the furnace itself.
Okay, so it's like giving the metal a hot bath to relax its muscles.
That is a great way to put it. The heat allows the atoms to recrystallize and arrange themselves into a uniform, stress-free lattice. It makes the steel softer and much more ductile.
Got it.
So when we test annealed mild steel in a laboratory, we're seeing the pure, unadulterated behavior of the iron-carbon matrix.
Okay, so we have this relaxed, pristine piece of steel. We put it in a testing machine and start pulling it apart. We pass the elastic limit. What happens next?
You see a phenomenon that is almost unique to this specific type of steel. The stress-strain curve goes up perfectly straight, but then it hits a peak.
The upper yield point.
Right, and suddenly, without you adding any more pulling force, the material actually gives way. The internal resistance drops rapidly to a lower value, which we call the lower yield point.
Wait, hold on. So the stress actually decreases even though the machine is still pulling it apart.
Yes. The material suddenly elongates significantly at this lower stress level. It just keeps yielding, stretching out at a roughly constant stress for quite a while.
Before it finally fights back.
Exactly.
Yeah.
Eventually, the internal structure rearranges itself enough to start resisting again, a phase called strain hardening.
Okay, let me process that. If I'm designing a bridge and I have this material that can technically hit a high peak, that upper yield point, before it starts permanently stretching, wouldn't I want to use that high peak as my maximum allowable limit?
It's very tempting to think that way.
Right. It seems like leaving performance on the table if we don't.
It does, but relying on the upper yield point is a classic trap that leads to catastrophic failures. And here's the why behind that. You have to consider the difference between a pristine laboratory environment and the messy, chaotic reality of a construction site.
Oh, I see where this is going.
Yeah. In a lab, testing machines are precision machined to ensure the load is applied perfectly axially, dead center down the middle of the specimen.
Because if it's perfectly centered, every single crystal of steel in that cross-section is feeling the exact same amount of pull at the exact same time.
Precisely. Under perfect conditions, the entire cross-section hits that upper yield point simultaneously. But in the real world, nothing is perfect.
Right. A steel beam in a building will have microscopic flaws.
Or the bolts connecting it might be slightly off-center. Or a heavy truck driving over a bridge applies the load slightly to one side. We call these eccentricities.
So in reality, one edge of the beam is going to be pulled just a tiny bit harder than the rest of the beam.
Yes. Because the stress distribution is non-uniform, that highly stressed edge will hit the upper yield point before the rest of the material does.
Oh, wow.
And remember what happens at the upper yield point? The resistance drops. So that tiny edge suddenly gives way and drops to the lower yield stress.
Which means it instantly transfers the load it was carrying to the adjacent crystals.
Exactly, pushing them past the upper yield point, causing them to fail and drop their stress.
It's a cascade failure, a domino effect running right across the steel beam.
That's exactly what it is. Once a microscopic area hits the upper yield point, you trigger a localized collapse that rips through the cross-section. Therefore, the upper yield point is an illusion of strength.
It's a fragile state that requires perfect conditions.
Right. The lower yield point, however, is stable. It is a much safer, vastly more realistic baseline for continuous yielding in structural design.
That makes total sense. You have to design for the worst-case scenario of real-world physics, not the best-case scenario of a laboratory test. Okay, still on the topic of pulling things apart, I want to talk about ductility. We know some materials stretch a lot before they break, like copper, and some just snap instantly, like cast iron or glass. When an engineer says a material is ductile, how are they actually measuring that?
Well, there are two primary ways to measure ductility after a specimen has been pulled until it fractures. The first is looking at the percentage reduction in the cross-sectional area.
Okay, how does that work?
When a ductile material fails, it doesn't just snap cleanly, it undergoes what we call necking. The middle of the specimen thins out significantly before it finally tears apart.
Like pulling a piece of gum.
Yeah, exactly. So you measure the area of that broken, thinned out neck, compare it to the original thick area, and calculate the percentage drop.
Makes sense. And the second way?
The second way is the percentage increase in overall length. You make 2 little scratch marks on the specimen before you test it, say, 2 inches apart. After it breaks, you fit the 2 broken halves back together, measure the distance between those scratch marks again, and calculate how much longer it got.
So if my 2-inch gap is now 3 inches, it's stretched 50%. Simple enough. But our source material points out a massive caveat here, something that throws a wrench in comparing these numbers.
Oh, absolutely.
The actual shape of the piece of metal you test drastically changes the result you get.
It alters it completely. Let's think about the physics of that necking process we just discussed. The severe stretching and thinning out happen in a very localized area right around the eventual break.
Right.
The rest of the parts further away from the break only stretch a little bit uniformly.
Ah, I see where this is going. If I use a test specimen that is very short and thick, the neck is going to take up a massive percentage of the overall length.
Right. And therefore, the percentage increase in length will appear to be very high. But if you test the exact same material using a long, thin wire, the localized necking zone is only a tiny fraction of the total length. The long sections of wire on either side of the break barely stretch at all compared to the neck. So if you measure the overall percentage increase in length for the long wire, it will be much, much lower than the short, thick specimen.
Even though it's the exact same metal from the same batch.
Yeah.
That is fascinating. It means a raw percentage number is totally useless unless you know the shape of the metal that was tested.
Which is exactly why international engineering standards exist. Organizations dictate exact standardized proportions for test specimens.
So everyone is on the same page.
Right. Specifically, the ratio between the gauge length and the cross-sectional area. You cannot ethically or scientifically compare the ductility of an aluminum alloy tested in Germany with a steel alloy tested in Japan unless both labs use geometrically similar test pieces.
That is wild. Okay, so we've stretched the material, we've measured how long it gets, but anyone who has ever played with a piece of taffy or like silly putty knows that you can't just stretch something in one direction without paying a price in another direction.
No, you can't.
When you pull taffy, it gets longer, but it also gets visibly thinner in the middle.
Right. And this brings us to a fundamental property of matter called Poisson's ratio. It describes lateral strain. When you apply a longitudinal pull to a bar, the bar elongates, but simultaneously the sides of the bar contract inward.
Okay.
For most structural metals operating in their elastic range, that lateral contraction is directly proportional to the longitudinal extension.
So I pull it twice as far, it gets twice as skinny.
Yes. The ratio of the lateral strain divided by the longitudinal strain is a constant for any given material. We call it Poisson's ratio, usually represented by the Greek letter nu. For common metals like steel or aluminum, this ratio hovers around 0.3.
Okay, so it gets longer and it gets skinnier. But what happens to the total amount of stuff? Like, what happens to the volume? If I have a cubic inch of steel and I stretch it, does it stay exactly 1 cubic inch, just in a different shape?
That is a profound question, and the answer is no. Stretching a metal actually changes its volume. We call this volumetric strain.
Okay, how do we calculate that?
The mathematical equation for this is incredibly elegant. The change in volume divided by the original volume is equal to the longitudinal strain multiplied by the quantity of 1 minus 2 times Poisson's ratio.
Okay, let me stop you, because I love looking at equations not just as math, but as, like, boundaries for reality.
Yeah.
Let's look at that multiplier. 1 minus 2 times Poisson's ratio.
Sure, let's run the numbers. If Poisson's ratio is 0.3, then 2 times 0.3 is 0.6.
Okay.
1 minus 0.6 leaves us with a positive 0.4. Since the multiplier is positive, a tensile pull results in a positive volumetric strain. The volume of the steel actually increases slightly when you stretch it.
The atoms are literally taking up more space. But wait, what if Poisson's ratio was higher? What if it was 0.5?
Well, if Poisson's ratio is 0.5, 2 times 0.5 is 1. 1 minus 1 is 0. That would mean the volumetric strain is 0. The material could change shape, but its volume would remain perfectly constant.
Like stretching a block of solid rubber, or squishing a balloon filled with water. The shape changes, but the volume doesn't.
Right.
Now, let's push the math over the cliff. What if a material had a Poisson's ratio of 0.6?
Okay, let's follow the logic. 2 times 0.6 is 1.2. 1 minus 1.2 is a negative number. This is where the mathematical formula acts as a guardrail for the laws of physics.
Because if the multiplier is negative, then pulling on the material would make its volume shrink.
Exactly.
But even crazier if you squished it, if you applied compressive stress, a negative multiplier would mean the volume would increase.
Exactly. Imagine taking a block of this hypothetical material and submerging it deep in the ocean, subjecting it to immense hydrostatic compressive stress from all sides. If Poisson's ratio exceeded 0.5, the equation dictates that the material would actually expand and increase in volume while being crushed by the water pressure.
Which violates the conservation of energy. And just common sense, you can't squeeze something from all sides and have it grow.
No, it is a physical impossibility for isotropic materials. Therefore, the mathematically prove that 0.5 is the absolute physical ceiling for Poisson's ratio. The universe simply doesn't allow a material to exceed that number.
I absolutely love that. The math isn't just a suggestion, it's the operating system of the universe.
That's a great way to put it.
Okay, now let's throw a wrench into all this stretching and squishing. Let's add heat, temperature, and initial stresses. The source material gives us a classic engineering puzzle that trips up a lot of students.
Oh, the bolt and tube problem.
Yes, imagine you have a hollow steel tube. You pass a solid bolt straight through the center of the tube, put a washer and a nut on the end, and tighten it down securely. At room temperature, everything is happy. But then you take a blowtorch and heat the whole assembly up by 100 degrees. What happens?
Well, the first thing you have to look at is the material composition. If the bolt and the tube are both made of the exact same type of steel, they possess the same coefficient of linear expansion.
Okay, and that means?
This coefficient dictates exactly how much a material expands for every degree of temperature increase. If they are the same material, the bolt lengthens by a certain amount, and the tube lengthens by the exact same amount. They expand together in perfect harmony. No new internal stresses are created.
But engineering is rarely that convenient. What if the central bolt is made of aluminum and the outer tube is made of steel?
That changes the game entirely because aluminum and steel have vastly different coefficients of linear expansion. Aluminum's coefficient is much higher. It is far more sensitive to temperature. So when you heat the assembly, the aluminum bolt desperately wants to expand and get much longer. The steel tube also wants to expand, but at a much slower rate.
So the aluminum is trying to stretch out, but the steel tube is holding it back, basically acting like a cage.
Yes. And conversely, the expanding aluminum is pushing outward on the nuts at the end of the tube, trying to forcibly stretch the steel tube beyond its natural thermal expansion. They are fighting each other.
Wow.
Because they are bolted together, they must eventually arrive at a compromise length.
How do you even begin to calculate who wins that fight?
You use what engineers call a compatibility equation. You start by calculating the free length of both materials, basically how long each one would be if they weren't bolted together.
Okay.
So you calculate the hot length of the aluminum and the hot length of the steel. You now have a gap. They disagree on what the new length should be. The compatibility equation states that this thermal difference must be perfectly offset by mechanical deformation.
Meaning the forces have to balance out to bend them to the same final dimension.
Exactly. The final compromise length will be somewhere between the two free lengths. This means the aluminum bolt is being physically compressed from its preferred free length down to the compromise length. It is now under severe mechanical compressive stress.
While being heated.
Right. Meanwhile, the steel tube is being physically stretched from its preferred free length up to the compromise length. It is under severe mechanical tensile stress.
So just by heating up a part resting on a table, you've created massive internal forces trying to tear it apart. You know, I read a fantastic real-world example of this involving the SR-71 Blackbird spy plane.
Oh, a legendary engineering challenge.
Right. The plane was built out of titanium, and it flew so fast over Mach 3 that the friction of the air heated the skin of the plane to hundreds of degrees.
Right.
If they had bolted the titanium panels tightly together on the ground at room temperature, the massive thermal expansion at Mach 3 would have caused the panels to fight each other, buckle, and just rip the plane apart in midair.
Absolutely.
So the engineers deliberately designed the panels to fit loosely on the ground. They literally left gaps, which meant that when the plane was sitting on the runway, its fuel tanks, which were integrated into the skin-leaked jet fuel all over the tarmac.
It's true.
It was only when the plane accelerated and heated up that the titanium expanded, the gaps closed, the metal sealed tight, and the plane became a rigid structure. They used the thermal expansion as a structural design feature.
That is a brilliant application of understanding the compatibility equation. They designed a structure that only achieved its intended geometry when under massive thermal load.
Okay, so we've stretched wires, we've heated up bolts, we've established the absolute ground rules of tension and compression. Now, I want to take a beam and lay it horizontally across a gap and stand on it.
Ah, moving into bending.
Yes, we are entering the bending world. Because when you bend a beam, you don't just get tension and compression. There is a hidden, insidious force sliding through the material, shear.
Shear is arguably the most misunderstood force in basic mechanics. To visualize it, think of taking a thick paperback book or like a deck of playing cards and bending it into a U shape.
Okay, I can picture that.
If you look at the edges of the pages, they slide past one another. The pages on the inside of the curve stick out further than the pages on the outside.
Because the inner curve is a shorter distance than the outer curve.
Exactly.
Yeah.
Now imagine if those pages were all glued together into one solid block of wood. The geometry still wants the layers to slide past each other to achieve that curve, but the glue prevents it.
Okay.
That tendency to slide and the internal resistance against it is horizontal shearing stress. And what is vital to understand is that this shear stress is not spread evenly through the depth of the beam.
So if I have a solid rectangular wooden beam, the shear stress isn't just an average number from top to bottom.
Not at all. The distribution of shear stress across a rectangular cross-section forms a perfect parabola. Let's map it out. At the very top edge of the beam, the shear stress is exactly 0. At the very bottom edge, it is exactly 0.
Hold on, why is it 0 at the edges? Wouldn't the outermost layers want to slide the most?
They want to, yes, but stress is a reaction to a constraint. At the free upper surface of the beam, there is no material resting on top of it to provide a complementary opposing shearing force.
I see.
Without an opposing force, there can be no internal stress. Therefore, shear must be 0 at the free boundaries. As you move from the top edge down into the meat of the beam, the shear stress increases along a parabolic curve. It reaches its absolute maximum peak exactly at the neutral axis.
Okay, let's define the neutral axis. If I bend a beam, the top half is being squished together, compression. The bottom half is being pulled apart, tension.
Right.
The neutral axis is that invisible horizontal dividing line running right through the center of the beam where the material is transitioning from compression to tension. At that exact line, the material isn't being stretched and it isn't being crushed. The direct stress is 0.
Yes. But as we just established, while the tension and compression are 0 at the neutral axis, the shear stress is at its absolute maximum peak. The center of the beam is doing nothing to resist the bending moment, but it is taking the maximum punishment from the sliding shear forces.
That is wild. And this completely explains the shape of an I-beam. I've always looked at the steel skeleton of a skyscraper and wondered why they use that distinct I shape instead of just solid, square blocks of steel. It's an optimization of these exact physics.
It is the physical manifestation of the math. Let's break down the geometry of an I-beam. You have two wide horizontal plates, the flanges located at the extreme top and extreme bottom,
Okay.
and they are connected by a thin vertical plate called the web. Why put all the heavy metal at the top and bottom? Because bending stress, tension, and compression is highest at the extreme edges.
Right.
The flanges exist entirely to handle the massive push and pull of the bending moment. They are placed as far away from the neutral axis as geometrically possible to give them the most leverage.
But the thin vertical web in the middle.
The web is sitting right on the neutral axis. Its primary job is not to resist bending. Its job is to handle that massive, peaking, parabolic shear stress. The web prevents the top flange from sliding horizontally past the bottom flange. By adopting the I-shape, engineers have literally carved away all the inefficient, heavy material that used to sit between the neutral axis and the edges, creating a shape where every ounce of steel has a specific, mathematically optimized job.
It's beautiful.
Yeah.
But I have a challenge for you.
Okay, go ahead.
An I-beam is perfectly symmetrical. The mass balances perfectly. What if the shape isn't symmetrical? What if I take an I-beam and slice it in half down the middle, leaving me with a C-shaped channel section? It's open on one side.
Right, a very common shape.
If I lay that C-channel horizontally to support a floor, and I push straight down on the top of it, right through its center of gravity, what happens?
This is a scenario that has caused many structural failures because it defies basic intuition. If you apply a vertical load straight down through the geometric center of gravity of an asymmetrical C channel, the beam will bend downward, yes,
Okay.
but it will also violently twist. It will rotate along its longitudinal axis.
Which is a nightmare. If you are building a floor, you want the joists to bend a little underweight, but if they twist, the entire floor deck rips off the nails and the structure collapses. Why does it twist if I'm pushing straight down on its center of balance?
To understand the twist, we have to look at how the shear forces flow through the material. In an I-beam, the shear forces in the top flange and the bottom flange flow in opposite directions, canceling each other out perfectly.
Okay, that makes sense.
But in a C-channel, the shear forces flow through the top flange, down the web, and back along the bottom flange. This creates a one-sided internal torque, a twisting moment generated entirely by the material's internal resistance to shear.
Okay, so the beam is generating its own internal rotational force just by trying to hold up the weight. That is crazy. How do we stop it from twisting?
To bend a C-channel without twisting it, you cannot apply the load at its center of gravity. You must offset the load. You have to apply the downward force at a very specific calculated coordinate called the shear center.
The shear center.
Right. By pushing down at an offset distance, your external load creates an external torque that perfectly opposes and cancels out the internal torque generated by the shear flow.
So I have to intentionally load it off-center to keep it stable. Where is this shear center on a C-channel?
What is truly fascinating here is that for a C-channel, the math places the shear center outside the physical bounds of the material.
Wait, what?
It is a point floating in empty air, situated behind the flat back of the web, on the side opposite the two protruding flanges.
Wait, you are saying the exact point where I need to push to keep the beam stable isn't even touching the beam?
That is correct.
Yeah.
If you were welding a support bracket to this C-channel to carry a heavy load, you couldn't just weld a hook to the web. You would have to design a bracket that physically reaches out into empty space, curving around to align the downward pull of the load perfectly with that invisible floating shear center.
That is unbelievable.
If the line of force passes through that point in the air, the beam will bend beautifully without a single degree of twist.
I love when the math demands a physical absurdity, but it's the only way to make the structure survive. Okay, let's add another layer of complexity, mixing materials. Let's talk about composite beams.
Ah, great topic.
Imagine I'm renovating a 100-year-old warehouse. I have these massive old timber floor joists. I need them to carry heavier modern machinery, so I decide to bolt thick steel plates to the sides of the wooden joists to reinforce them. How on earth do you calculate the safe load for a beam when you have two completely different materials fighting the exact same force?
It is a complex problem because wood and steel respond to stress very differently. To solve it, engineers use a brilliant mathematical trick called the transformed section method. First, we have to make an assumption.
Okay, what's that?
We assume the steel plates are bolted so tightly to the timber that they cannot slip. They act as one single unit. Therefore, when the beam bends, they must bend to the exact same radius of curvature.
Right, if they bent differently, they would tear the bolts out, so they curve
Mm.
together.
Because they curve together, the geometry dictates that the longitudinal strain, the physical stretching or compressing, at any specific height from the neutral axis must be identical for both the wood and the steel. They stretch the exact same amount.
But getting steel to stretch a millimeter requires vastly more force than getting pine wood to stretch a millimeter.
Precisely. And this is where we bring in Young's modulus. Young's modulus is the fundamental measure of a material's stiffness. It is the ratio of stress over strain in the elastic region.
Okay.
Steel has a Young's modulus roughly 20 to 30 times higher than timber. It is vastly stiffer. So even though the wood and the steel are stretching the same distance, the steel is carrying 20 to 30 times more stress to achieve that stretch.
So how do we put that into a single usable math equation?
We calculate the modular ratio, which is simply the Young's modulus of the stiffer material divided by the Young's modulus of the weaker material. Let's say the modular ratio of steel to wood is 20. To simplify the incredibly complex calculus of two materials, we mathematically eliminate one of them. We transform the steel plates into an equivalent piece of timber. Because the steel is 20 times stiffer, we pretend the steel isn't there and replace it with imaginary wood that is 20 times wider than the steel plate was.
Wait, so if my steel plate was half an inch thick, I do my math as if I have an extra 10 inches of wood bolted to the side.
Exactly.
It's a phantom beam. You create an imaginary giant wooden beam that behaves structurally identically to the real composite beam. That is a fantastic mental shortcut. And this same concept applies to the most common composite material on Earth.
Reinforced concrete, right. It does, but with a severe twist. Concrete is an incredible material under compression. You can stack a skyscraper on it. But under tension, it is practically useless. It cracks and fails almost immediately when you try to stretch it.
Right.
So when a concrete beam bends, the top half is happily taking the compression, but the bottom half wants to tear itself apart. To fix this, we embed steel rebar into the bottom of the mold before we pour the concrete.
So the steel handles the pulling, the concrete handles the crushing. But how do you use the transformed section method if one of the materials literally cracks and fails?
You have to make a bold, somewhat terrifying assumption in your calculations. You completely ignore the existence of the concrete on the tension side of the neutral axis.
You just pretend it's not there.
You assume it has cracked and is contributing absolutely zero structural strength. It is just dead weight hanging there to protect the steel from fire and rust.
So mathematically, the bottom half of the beam is just empty space with some steel rods floating in it.
Mathematically, yes. You take the cross-sectional area of those steel rods, multiply it by the modular ratio of steel to concrete, which is usually around 15, and transform the steel into an equivalent block of imaginary, super stiff concrete located at the exact depth of the rebar.
Wow.
You balance the area of the real concrete in compression at the top against this equivalent area of phantom concrete at the bottom to locate the true neutral axis. You are designing a real building using the geometry of a ghost structure.
I'm starting to realize that structural engineering is half physics and half highly sanctioned hallucinations.
Well, mathematically sanctioned hallucinations, yes.
Okay, let's shift gears from what beams are made of to how we hold them up. If I place a wooden plank across a creek, resting on the banks, that's a simply supported beam. But the text discusses built-in or fixed beams.
Right.
If I embed the ends of a steelary, I beam deeply into two massive, unmoving concrete walls. The ends of the beam cannot rotate when weight is applied. Our deep dive sources say this makes the beam significantly stronger and stiffer. The maximum bending moment drops dramatically compared to the simply supported plank.
That is correct.
So my question is, if building it into the wall makes it mathematically stronger, why don't we just build in every single beam in every structure? Why leave anything simply supported?
Because in engineering, you never get something for nothing. If we look at the bigger picture of how buildings exist in the real world, built-in beams come with a devastating penalty. They are hypersensitive to changes in their environment. When you rigidly fix the ends of a beam, you are betting the safety of the structure on the assumption that those massive concrete walls will never, ever move, not even a fraction of an inch.
But the ground settles. Subsidence happens all the time.
Exactly. Let's look at the simply supported plank across the creek. If the left bank sinks down an inch, what happens to the plank?
It just tilts.
Right, it slopes slightly. The internal stresses in the wood don't change at all. It's perfectly safe. But now, imagine our rigidly built-in steel I-beam. If the left concrete wall sinks by 1 inch, the wall doesn't just lower the beam. The rigid connection forces the end of the beam to remain perfectly horizontal as it drops.
Oh, well, so the left end is horizontal but lower. The right end is horizontal but higher. The beam has to violently twist itself into an S-curve just to connect the two ends.
Yes. A tiny sinking of one support induces immense, catastrophic internal bending moments, completely independent of whatever weight the beam was supposed to be carrying. The structure literally tears itself apart, just trying to accommodate a slight shift in the foundation.
That's horrifying.
And the same vulnerability applies to temperature. If a built-in beam heats up and tries to expand, the rigid walls won't let it. The beam acts like a massive hydraulic ram, either buckling itself or pushing the concrete walls over.
So by making the connection rigid to gain localized strength in the beam, you've created systemic fragility for the entire building. The cure is worse than the disease. Is there a compromise? A way to get the strengths without the hypersensitivity?
There is an elegant solution called the double cantilever construction. Let's map out the bending forces on a rigidly built-in beam. Because the walls are preventing the ends from rotating, the bending moment at the walls is actually negative. The beam is trying to bow upwards.
Okay.
But in the middle of the span, the weight is pushing it down, so the bending moment is positive.
Wait, if the bending moment goes from a negative number at the wall to a positive number in the middle, it has to cross zero somewhere.
Precisely. Mathematics dictates that there must be a point, actually 2 points, one on each side, where the bending moment transitions through zero. We call these the points of contraflexure. Since the internal bending stress is zero at these exact locations, engineers will literally cut the massive steel beam entirely in half at those points.
You deliberately sever the main load-bearing beam.
Yes. You cut it, and you install physical articulating steel hinges connecting the cut pieces. Because the bending moment was zero there anyway, the hinges don't weaken the load-carrying capacity of the design. The structure still behaves like a strong built-in beam.
Oh, I see.
But if the left wall suddenly sinks by an inch, those hinges act like elbows. They articulate. They allow the structure to flex and adjust to the shifting foundation without inducing those catastrophic S-curve bending moments.
That is just brilliant, finding the mathematical zero point and exploiting it to introduce physical flexibility. Okay, we need to transition into part 3. Combined stresses. We've talked about beam sagging and we've talked about wires pulling. But what happens when you combine them? What happens when you take a beam, stand it straight up vertically like a Greek column, and crush it? But the crush isn't perfectly centered.
We call that eccentric loading, and it is a fundamental challenge in designing anything tall and heavy. Imagine a tall, square masonry pier made of brick and mortar. And on top of this pier, you place a massive, heavy bronze statue.
Okay.
But whoever placed the statue didn't put it dead center. It's offset towards the right edge. That eccentric thrust creates two distinct simultaneous stress profiles.
Walk me through them.
First, gravity is gravity. The sheer weight of the statue creates a uniform, direct compressive stress across the entire cross-section of the brick pier. It is squishing every single brick downward equally.
Right.
But second, because the statue is off-center, it acts like a lever arm. The offset weight creates a bending moment. It is trying to tip the top of the pier over to the right.
Okay, so it's crushing it and is bending it at the same time.
Exactly. Now let's combine the stresses. On the right side of the pier, the statue is leaning toward the compressive stress from the raw weight, adds together with the compressive stress from the bending. That side is getting doubly crushed. Bricks are very strong in compression, so it will likely survive.
But look at the left side, the back of the pier.
Exactly.
The direct weight is trying to crush it, but the bending moment is trying to stretch it upward. The bending is putting the left side into tension.
And earlier we established that things like concrete and masonry absolutely hate tension. If the tension from the bending is stronger than the downward crush of the gravity, the mortar joints on the left side will rip open and the whole pier will topple over.
That is the exact failure mode. Therefore, the cardinal rule of designing unreinforced masonry structures, whether it's a brick column or a stone cathedral wall, is ensuring that the tensile stress generated by the bending moment never, ever exceeds the compressive stress provided by the raw weight.
Yes.
We need the entire cross-section from left to right to remain constantly squeezed in compression.
That is absolutely vital.
So how do you guarantee that? Do you just keep adding more weight to the top to overpower the tension?
You manage the geometry. To ensure zero tensile stress, the downward load must be applied within a very specific, mathematically defined central zone of the column's cross-section. We call this central safe zone the core of the section. If the load wanders outside this core, tension develops on the far edge and the structure fails.
And the math for this core translates into one of the most famous rules of thumb in all of engineering, right?
Yeah.
The middle third rule.
Yes. For a solid rectangular column, we can derive the boundary of the core mathematically. We equate the formula for direct stress force over area with the formula for maximum bending stress.
Okay.
When we solve for the maximum allowable eccentricity, the maximum distance the load can be offset from the center before tension occurs, the answer simplifies beautifully to d divided by 6, depth over 6.
So from the exact center, you can move the load 1/6 of the total width to the right or 1/6 of the width to the left. 1/6 plus 1/6 equals 2/6, which reduces to 1/3.
Exactly. The safe core is the central 1/3 of the column's width. As long as the thrust line of the load stays within that middle third, the entire column remains in compression and the mortar stays intact.
It's incredible to think that medieval cathedral builders instinctively understood this when designing flying buttresses. They didn't have the equation for eccentric loading, but they knew they had to push the massive outward thrust of the heavy stone roof back into the central core of the stone walls to keep them from blowing outward in tension.
It is the exact same principle. They used the mass of the buttresses to redirect the force vector so it passed safely through the middle third of the supporting piers down to the earth.
That is so cool. But what if we don't want to just avoid tension? What if we want to aggressively use this concept of combined stresses to our advantage? This leads us perfectly to the modern miracle of pre-stressed concrete.
Pre-stressed concrete is arguably one of the greatest leaps in construction technology of the 20th century. We already discussed the tragic flaw of normal reinforced concrete. The concrete on the tension side of the beam inevitably cracks under load, rendering it structurally useless.
Right.
Engineers wanted to find a way to make the whole beam work. The solution was to cheat the physics by introducing artificial internal stresses before the beam ever leaves the factory.
Explain how that works on the factory floor.
Imagine the long steel mold for a highway overpass beam. Before any concrete is poured, engineers run thick, high-tensile steel cables tendons through the lower half of the mold. They attach immense hydraulic jacks to the ends of these cables and pull them incredibly tight, stretching the steel.
Like tuning a guitar string.
Exactly. And while the cables are held under this massive tension, the concrete is poured around them and allowed to cure until it is solid stone.
And then they release the hydraulic jacks.
Yes. They cut the cables at the ends of the beam. The highly stretched steel tendons immediately try to snap back to their original length like giant rubber bands. But they can't because they are now firmly bonded to the cured concrete.
Oh, wow.
As the steel tries to shrink, it aggressively compresses the concrete around it.
So the concrete is being violently crushed by its own internal skeleton.
Crucially, it is being crushed eccentrically. Because the cables are located in the bottom half of the beam, the bottom edge is subjected to massive compressive stress. It often causes the entire beam to visibly bow upwards in the middle, cambering like a bridge. We have deliberately preloaded the bottom of the beam with a massive reservoir of compressive stress.
I see. It's like prepaying your structural debt.
That's exactly what it is.
When you finally take that beam out to the highway, install it, and drive a line of heavy semi-trucks over it, the weight of the trucks bends the beam downwards. It tries to stretch the bottom of the beam into tension. But before the load can actually put the concrete into tension and crack it, it first has to overpower and cancel out all of that massive pre-compression we artificially injected.
Exactly. We calculate the exact maximum bending moment the trucks will cause, and we inject the precise counteramount of pre-compression. Under maximum load, the bottom of the beam just reaches zero stress. It never actually enters tension.
That is genius.
The concrete never cracks. The entire depth of the beam remains active and structurally sound. This allows engineers to span vast distances, like long bridges or massive parking garage floors, with incredibly thin, elegant concrete structures that would have been impossible with traditional reinforced concrete.
Fighting forces with artificial forces. That is brilliant.
Yeah.
Okay, we have covered stretching, bending, and crushing. We need to transition into part 4. Torsion, the absolute complexity of twisting forces. Let's go back to our opening scenario. The massive steel drive shaft of a container ship connecting the engine to the propeller.
Torsion is fascinating because the deformation happens in a unique geometric pattern. Let's imagine a solid, perfectly circular steel shaft. If you were to draw a perfectly straight line along the length of the shaft with a marker and then apply a twisting torque to one end while holding the other end still, that straight line would distort into a helix curving around the cylinder.
Like candy cane stripe.
Right. The material is shearing, rings of atoms are sliding rotationally past adjacent wings of atoms.
And just like the bending beam earlier, this shear stress is not uniform, right?
Correct. The shear stress distribution in a twisting circular shaft increases linearly from the center. At the absolute dead center longitudinal axis of the shaft, the radius is 0, so the twisting motion is 0, and therefore the shear stress is exactly 0. As you move radially outward from the center towards the skin, the shear stress increases in a straight line, reaching its absolute maximum severity at the outer surface.
Wait a minute. If the stress is 0 at the center and only reaches its peak at the outer skin, that means the vast majority of the solid steel core inside that ship's drive shaft is basically just going along for the ride. It's doing barely any work to resist the twist.
You have just hit upon a major realization in mechanical engineering. In a solid circular shaft, the core adds immense heavy mass, but contributes very little to the torsional strength.
Wow.
This inefficiency directly leads to the widespread use of hollow circular shafts. If you bore out the center of the shaft, creating a thick-walled pipe, you are removing material that wasn't carrying much stress anyway.
So a hollow pipe is stronger than a solid bar.
Not strictly stronger, but vastly more efficient. Our deep dive sources highlight a specific mathematical comparison. If you have a solid steel shaft carrying a certain torque and you replace it with a hollow shaft that has the same outer diameter but a bored out center, you maintain nearly all of the torsional strength because the highest stresses are handled by the outer ring of material.
That's incredible.
By optimizing the inner and outer diameters to maintain the exact same maximum allowable shear stress, engineers achieved a 21% mass savings.
21%. In the context of a ship, an airplane, or even the drive shaft of a heavy-duty truck, saving 21% of the weight of a massive rotating steel component is an incredible gain in fuel efficiency and performance. You are carrying the exact same torque with significantly less penalty.
It is optimization through geometry. And for circular shapes, the math is incredibly cooperative because of radial symmetry. Cross-sections of a circular shaft remain perfectly flat, plane surfaces during the twisting motion.
Okay, so circles are the ideal shape for twisting. But engineering is messy. Sometimes you can't use a circle. What if a mechanism requires twisting a square bar or a triangular shaft?
This is where classical intuitive mechanics completely break down. The rules we just established for circles do not apply to non-circular shapes.
Why not?
When you twist a square bar, the cross-sections do not remain flat. The flat planes literally warp. The corners of the square distort longitudinally, puckering in and out along the length of the bar.
The geometry physically folds. Why does that happen?
Because the shear stress cannot be uniform radially. The corners of a square are further from the center than the midpoints of the flat sides. Because of this complex warping behavior, the standard geometric property we use for circles, the polar second moment of area, which measures a shape's resistance to twisting based on its area distribution from the center, becomes entirely useless.
It completely fails to predict the stress.
It fails completely and dangerously. If you use the circular formula on a square shaft, you will underpredict the maximum stress by a massive margin, and the shaft will fail. To calculate the twist of a square or a triangle, the simple polar moment must be replaced by a highly complex, shape-specific torsional constant denoted as J.
And how do you find J?
Finding J for complex, non-circular shapes requires solving advanced partial differential equations. Specifically, Poisson's equation or Laplace's equation mapping the complex warping functions across the boundaries of the shape.
And solving those multivariable differential equations by hand in the early 20th century, before supercomputers, was an absolute nightmare for engineers.
Oh, absolutely.
Which brings up what is honestly my favorite concept in this entire deep dive: Prandtl's membrane analogy. The German physicist Ludwig Prandtl realized a shortcut. He realized that the nightmare math for a twisting square was identical to the math describing a soap bubble. Please unpack this analogy for us. How does a bubble solve a steel problem?
It is a true masterpiece of lateral interdisciplinary thinking. Prandtl recognized a mathematical coincidence. He saw that the differential equation governing the complex shear stress distribution in a twisting non-circular shaft was mathematically identical in structure to the differential equation describing the upward deformation of a thin, weightless elastic membrane stretched over a hole and pressurized from underneath.
So the math is the same, just describing two totally different physical phenomena. How did they actually use this in a lab? Did they actually blow bubbles?
They did. To solve the stress of a bizarrely shaped structural component, engineers would take a flat metal plate and precisely cut a hole in it, matching the exact cross-sectional shape of the component, say, a star shape or a square.
Okay.
They would stretch a soap film tightly over that hole. Then they would apply a very slight, carefully controlled air pressure from underneath the plate, causing the soap film to bulge upward into a subtle dome.
A physical analog calculator made of soapy water. How do you translate the shape of the bubble back into the stress of the solid steel?
The physical translation is beautifully direct and relies on 3 rules. First, if you shine a light and map the contour lines on the bulging soap bubble lines of equal elevation, like on a topographic map, those lines indicate the exact direction of the shear stress flowing through the twisted metal cross-section.
Okay, direction is rule 1. What about the magnitude of the force? Where's it going to break?
That is rule 2. The magnitude of the shear stress at any specific point in the metal is directly proportional to the steepness of the soap bubble at that corresponding point. The steeper the angle of the soap film, the higher the shear stress.
Amazing.
And rule 3. The total volume of air trapped underneath the bulging bubble is directly proportional to the total torque the shaft is currently carrying.
That is staggering. Before digital modeling, engineers could use a micrometer to measure the slope of a soap bubble to map the invisible stress concentrations in a steel beam. And if you do this with a square hole, you see something completely counterintuitive. Where is the bubble steepest on a square?
If you pressurize a square bubble, the steepest slopes are at the exact midpoints of the four flat outer sides. As you move toward the corners, the slope flattens out, until at the very sharp corners, the slope is practically zero.
Which means the highest stress is in the middle of the flat sides, and the stress at the corners is zero. Common sense tells you the sharp corners would break first, but the soap bubble proves that if you twist a square steel bar until it fractures, the crack will start right in the middle of the flat edge.
Exactly. It defies intuition, but the fluid dynamics of the membrane perfectly mirror the solid mechanics of the metal.
Okay, but what happens when the twisting force goes past the elastic limit? What happens when the metal yields, hits that lower yield point we discussed earlier, and goes plastic everywhere? The soap bubble can't model a permanent plastic failure, right?
Right. The soap bubble relies on constant surface tension, modeling linear elastic behavior. When the metal hits its yield point and enters the plastic zone, the shear stress becomes constant. It reaches its maximum limit and cannot increase any further, even as the shaft continues to twist.
So if the stress is constant, and the stress equals the slope, in our analogy, then the slope must become constant. A bubble doesn't have a constant straight line slope. It's curved.
Exactly. So the membrane analogy evolves into what we call the sandhill analogy. Because the plastic shear stress is constant everywhere in the yielded material, the slope of our physical model must be a constant flat angle everywhere. What in nature forms a perfectly constant slope,
A pile of dry sand.
settling at its natural angle of repose.
Yes.
Yes.
So instead of blowing a bubble, we pour sand.
Yes. You take that same metal plate with the square hole, you lay it flat, and you gently pour fine, dry sand onto the shape. The sand will pour through the hole, but it will also pile up on top of the shape, naturally forming a mound with perfectly straight angled sides.
Okay, I'm visualizing this.
The ridges where the flat planes of sand intersect show you the exact internal boundaries between the different plastic stress zones inside the metal shaft.
And the total volume.
Just like the bubble, the total volume of that conical sandhill gives you the fully plastic torsional moment of resistance. It is a physical, granular representation of the ultimate failure state of the component. You calculate the catastrophic failure of a steel beam by measuring a pile of sand on a desk.
I am absolutely obsessed with the sandhill analogy. It represents the absolute peak of classical engineering ingenuity, using the observable natural world to solve invisible mathematical forces.
It really does.
But this brings us to a massive pivot. We are no longer pouring sand on desks. What does this all mean for the human beings actually doing the math today? We have moved from the raw physics to how we actually execute these designs across thousands of people. Part 5. Bringing it together, concurrent engineering. It is obvious that no single engineer does all of this math for an entire Boeing aircraft or of a Ford truck anymore.
No, it is impossible. The sheer volume of data, the interconnectivity of the parts, and the specialization required demand vast virtual networks of engineering teams. Traditionally, engineering was a sequential, almost isolated process.
Throwing it over the wall, right?
Right. Exactly. The aerodynamicist designs the sleek, perfect shape of a turbine blade and throws the CAD file over the proverbial wall to the structural engineer.
Okay.
The structural engineer runs the torsion and bending equations we just discussed, realizes the sleek blade will shear in half instantly, thickens it up to make it safe, and throws it over the wall to manufacturing.
And then manufacturing gets mad.
Manufacturing realizes the new thick blade is impossible to cast in titanium, so they altered the geometry again. By the time it is built, the aerodynamicist's original airflow goals are ruined. It was slow, adversarial, and incredibly expensive.
So the source material outlines the modern solution: concurrent engineering. Instead of sequential steps, all disciplines work simultaneously in a shared digital environment.
But wait, I have to push back on this.
If we were all working at once, how does that not descend into absolute chaos? If I am the mechanical engineer and I am setting strict structural constraints on the thickness of that turbine blade to manage the shear forces, and you are the aerodynamicist simultaneously tweaking the curves to improve airflow, reducing the thickness, we are fundamentally violating each other's work in real time. How do we not crash the entire million-dollar project?
That is the core vulnerability of concurrent engineering, maintaining consistency across highly coupled interrelated parameters. If we work simultaneously without oversight, we destroy the design. The solution, which the text emphasizes heavily, is the deployment of rigorous, automated constraint management systems.
Okay, how does a software system manage human disagreement?
Modern virtual teams use methodologies like QFD or quality function deployment. QFD is essentially a vast matrix, often called the house of quality, that maps subjective customer needs to objective engineering parameters.
Give me an example of how that mapping actually works.
Let's say the customer requirement is the airplane must have a range of 3,000 miles. That is the subjective goal. The QFD system breaks that down. Range requires low weight and high aerodynamic efficiency. Aerodynamic efficiency dictates a very thin, sharp wing profile.
Right.
So the software establishes a hard mathematical constraint. The wing thickness at coordinate x cannot exceed y millimeters.
But the structural engineer knows that if the wing is thinner than y millimeters, it violates the transform section modulus and will break under bending stress.
Exactly. And this is where the constraint manager acts as the referee. The software lives in the shared digital workspace. Both you, the structural engineer, and the aerodynamicist are working on the same cloud-based CAD model.
Okay, so we're in the same file.
Right. The aerodynamicist, chasing fuel efficiency, tweaks the spline curve of the wing, making it thinner. The moment they hit save, the constraint management software runs a background check against the QFD matrix. It instantly sees that the new dimension violates the structural minimum thickness constraint.
Does it just lock them out?
It flags it. It generates an immediate notification. If the aerodynamicist tries to push updates that violate your structural constraint multiple times, the system escalates the issue. It generates a conflict report showing exactly who violated what parameter by how much and what customer requirement is at risk.
Wow.
Crucially, the system will temporarily lock the finalization of that component and trigger a mandated, targeted meeting between the aerodynamics team and the structural team to negotiate a compromise. It forces human harmonization.
It's like having an omniscient digital Robert Hooke looking over everyone's shoulder, making sure no one breaks the laws of physics or the project rules.
Pretty much.
But I see another massive problem with this digital workflow. And it's something I complain about constantly when looking at old projects. The traditional engineering paper notebook is dead, but what replaced it is often worse. A paper notebook was covered in coffee stains, but it contained the engineer's methy thoughts. Today, a digital CAD file just shows the final dimension. It doesn't capture the 30-minute argument we just had over a video call about the shear center. The context is completely erased.
And that loss of context, what we call the design rationale, is incredibly dangerous and expensive for a corporation. This is why the sources stress the necessity of corporate history management services. A digital engineering ecosystem must capture far more than just the final geometrical drawing. It has to document the why behind the what.
Because 5 years later, when the next version of the jet engine needs an upgrade, the original aerodynamicist is retired, the structural engineer is moved to a different company, and the new team looks at this weirdly shaped, compromised turbine blade and asks, why on earth did they design it this way?
Exactly. And if they don't know why, their first instinct will be to fix it by streamlining it, unwittingly reintroducing the exact structural failure the original team fought so hard to avoid.
That happens all the time.
It really does. A proper history management system must support deep hyperlinking. When you click on the thickness dimension of that blade, it shouldn't just show a number. It should link to the specific QFD constraint that forced that thickness, link to the simulation data that proved a thinner blade would fail, and even link to the transcript of the video meeting where the compromise was reached. It captures the entire causal chain of logic.
It essentially archives the corporate memory, and the source text mentions a specific AI-driven technique used to leverage this archived memory. Case-based reasoning. How does that differ from just using a search bar?
It is fundamentally different because human problem solving is fundamentally different from computer searching. Computers are phenomenal at searching databases if you know the exact specific index keyword. But engineers facing a novel problem don't always know the keyword. Humans are great at analogy. We solve problems by recognizing patterns. We say, this new twisting vibration issue on the helicopter rotor reminds me of that weird resonance problem we had on the drone landing gear 5 years ago.
Yes. You remember the shape of the problem, but not the file name.
Right. But humans are terrible at actually finding that 5-year-old file among millions of gigabytes of corporate data. Case-based reasoning software bridges that gap. It indexes past designs not just by part names, but by their abstracted constraints, their design rationales, their failure modes, and the physics involved.
Okay, so how does an engineer use it?
An engineer can input the parameters of their current problem, say, high torsional shear in a constrained space, and the case-based reasoning system retrieves successful past geometries and solutions from entirely different product lines that faced analogous constraints.
So you use a digital brain to do the massive data fetching and the human brain to do the creative pattern matching. It prevents the team from reinventing the wheel, saving massive amounts of time and money by recycling proven, safe logic.
It is the pinnacle of the engineering process, ensuring that the hard-won lessons regarding yield points, shear centers, and complex torsion are never lost, but actively repurposed to solve the geometries of the future.
This brings us to a final provocative thought to wrap up this masterclass. Think about what we've covered today. We started with Robert Hooke in the 1600s, stretching a wire, and we ended with AI-driven, case-based reasoning. Modern engineering is this incredible, almost poetic marriage of unyielding physical laws, like the absolute fact that a non-circular shaft will inevitably warp under torsion, or that the lower yield point will trigger a cascade failure, married to highly adaptable, fluid digital workflows like concurrent constraint management. The real challenge for you, the modern engineer, whether you are building a bridge or a spacecraft, isn't just knowing how to solve the parabolic shear equation. The software can do that math for you. The true challenge is deeply understanding the why behind the physics and effectively communicating the rationale of your solution across a global virtual team before the design is set in stone. You are managing the raw laws of physics, but you are equally managing human alignment and corporate memory.
It truly is the ultimate synthesis of the natural world and human collaboration. Mastering both is what separates a technician from a master engineer.
Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.